Good afternoon, and thanks so much for joining me for this talk. My name is Will Benton, and I'm a software engineer at Red Hat. Today I'm going to talk about how my team's Spark deployment changed as our work with Spark matured. First off, though, I'd like to level set and get a little bit of a sense for your background. So how many people in here use Linux containers or Docker containers? Awesome. How about in production? It's good to see that those numbers are fairly similar. So Linux containers are a great way to package up applications and their dependencies and run them with some degree of isolation. But it can get tricky to orchestrate applications that are composed of multiple containers that might be running on different hosts. Kubernetes is a resource manager for applications that run on clusters of containers. It forms the basis for platforms like Google Cloud Platform, CoreOS Tectonic, and OpenShift. And most recently, it's been in the news because it runs some of the infrastructure behind the popular Pokemon Go game. The story I'm going to tell today is the story of how my team went from having a cluster for our analytics workloads to a cluster for our analytic applications, and what we had to do to get there. For a little more than 2 years now, I've been leading a data science team focused on emerging technology. We wanted to solve data problems that other groups within Red Hat had using cutting-edge open source tools and architectures. Our goals were enabling scale-out for machine learning pipelines that have been developed against small data sets on single machines, developing techniques that led to interpretable models that would tell us something about the world instead of just being a black box for predictions, and developing techniques that had improved predictive performance. We had Spark expertise, and we wanted to use Spark. Since we didn't have a legacy Hadoop deployment, we didn't bother with HDFS. We just used a networked POSIX file system. At the time, deploying on Mesos seemed like the best option. We knew that Spark and Mesos shared heritage, and that we'd get more control than running in a standalone cluster. We didn't seriously consider Yarn because we had no legacy Hadoop, and we weren't running anything other than Spark on Mesos, so we had no other Mesos frameworks on our cluster. This worked pretty well for development when we were prototyping new techniques and evaluating their scalability and model performance. We'd coordinate informally, figure out what each person needed for their work, and partition resources based on that. Things got a little more complicated when we wanted to share our work with collaborators and keep things running in production. Because of how we were running things, we either needed to create Unix users for our collaborators across our whole cluster, or get into some broader identity management. And having the focus on the Spark cluster as the shared resource didn't make sense once we started looking at long-term applications, putting our work into production. Once you're in production, you're not just making a program that you run to train a model and put up some graphs. You're providing an application that uses, supports, and depends on that model. Ultimately, we really ran into this theme. The ways we could deploy Spark to run analytics workloads made sense when we were running analytics as a workload. But analytics is no longer a separate workload. Today, we increasingly put analytics into production as an essential part of our applications. So we had a few goals in this effort to find a way to run our applications. We wanted to run Spark both for exploratory use and for production use. We wanted to be able to share our work and our cluster with collaborators without becoming expert system administrators or scheduler policy ninjas. And we wanted to provide a developer-friendly workflow for updating apps with continuous deployment. Here's what we'll cover in the remainder of this talk. We'll start with some background about microservices, which are an interesting trend in application development. Then we'll talk about what a data-driven application has to do, and look at a few architectural options for organizing these. Now, I think that getting the architecture right is really important for designing a modern, container-based, data-driven application, but we'll review some practical details of getting Spark to work well in containers as well. And finally, I'll close by showing you how you can try this yourself and show you where we're going next. We'll start by looking at microservices. So this may be a review for those of you who are using containers in production already, but I'll explain what I mean by a microservice architecture so everyone can be on the same page. This is just a way of structuring applications that instead of doing everything in a single monolithic service, we break our application down into multiple lightweight and typically stateless components with well-defined interfaces and contracts. Now, we do get some extra complexity by having to define these interfaces and orchestrate these components, but we get some compelling benefits in return. In particular, These stateless services are really easy to deploy and manage because they're a natural fit for running in stateless containers and on container orchestration platforms like Kubernetes. Stateless services are commodities. If one of them goes away, you can spin up another one to replace it trivially. Unlike bare metal nodes or stateful virtual machines, this means you don't have to care about the identities of the containers that are making up your application, just that some containers running certain services exist and are properly connected to one another. Stateless services are easy to scale out because you can spread them across multiple machines or even load balance by proxying requests to multiple copies of an individual service. Stateless services are easier to test and debug than stateful services. Instead of managing complicated test fixtures that set up a bunch of state before each test, or identifying minimal sequences of interactions to reproduce a problem, you can just ensure that each microservice returns the expected outputs for a range of interesting inputs. In this way, debugging microservices is really analogous to debugging pure functions running on immutable RDDs or data frames. So those are technical advantages, but there are also political and social advantages to microservices. It's harder to onboard new developers onto a big monolithic code base, and it's harder to diagnose performance or correctness problems in a big monolithic application. By contrast, if we divide an application up into simple communicating components that have explicit responsibilities, interfaces, and SLAs, it's much easier to scale out that team that's going to work on that application and for that team to be productive. Spark is actually already a really great fit for these kinds of elastic, stateless architectures. If we ignore caching, which is just an optimization, then a Spark executor is a stateless service that computes new partitions for RDDs or calculates values for actions. Sort of like that. Now, when one of these executors goes away, we know how to replace it from the lineage information of the RDD. In fact, even the Spark master can be replaced in a high availability configuration if we can store a small amount of state to enable a replica to pick up where the one that crashed left off. So if we want to take advantage of microservices, it's really crucial to get the architecture right. To provide context for these architectural choices, let's start by taking a high-level look at some of the responsibilities of a data-driven application. Fundamentally, a data-driven application does everything that a conventional application might do. The key difference is that this application also engages in data federation and processing. It transforms and aggregates data from multiple sources, trains predictive models based on that data, and uses those models to transform and make predictions from new and existing data alike, ultimately saving raw and processed data to archival storage. A data-driven application also needs to support a few different kinds of user interface. An internal-facing interface for developers and data scientists to perhaps install a new model or modify how existing models are trained, web and mobile interfaces for end users, a reporting and alerting interface for the business side, and a management interface for deploying, orchestrating, and monitoring the actual components of the application. So we're going to start our overview of architectures by looking at a couple of monolithic architectures that support analytics as a workload. In a traditional data warehouse, we federate data in a relational database that's optimized for fast concurrent updates. Our application processes a stream of transaction and user events, transforms these, maybe applying some business rules, and then updates the database. So we're going to call this the transaction processing part. And this is what holds the canonical information about the current state of our system. This is where we know how much inventory we have, how much money we have, so on. To extend this basic transaction processing application with analytic capabilities, we're going to periodically dump the contents of our transactional database to another database that's optimized for fast reads and complex queries. We'll use this database to support various kinds of analytical processing, primarily to support reports that project multidimensional data into easy-to-digest spreadsheets. We can also feed results from our batch analysis back to the business logic and allow analysts to do exploratory interactive queries against this database. We call this the analytic processing layer. You've probably seen this architecture before, right? It's been successful for a long time, but it's not perfect. On the transaction processing side, it's historically been really difficult to scale out transaction processing relational databases. So much so that people typically bought the largest machine they could possibly afford to run these things on, because you're not going to run a database on a cluster in most cases. High-performance relational databases are also difficult to manage. And finally, in this architecture, we don't have a canonical source for raw unprocessed data without some extra effort. And if you've ever had to change your pipeline once you put it into production, you know why you might want to have that raw data sticking around. On the analytic processing side, it's a lot easier to scale out if you're only supporting reads, right? In fact, you could use Spark for the analytic processing part of this architecture. But your results are still going to lag behind the canonical current state of the world as in your transaction processing system. And if you're using a relational database, you're limited to whatever capabilities it provides. And it can be really hard to implement model training code in SQL and procedural extensions to SQL. The data lake approach, as popularized by Apache Hadoop, federates data in a distributed scale-out file system. If you need to add more space, you add extra nodes to increase your storage capacity, and the expectation is that these will stick around for a while. As new events arrive, you just append them onto files in a distributed file system. Now, this raw data we're collecting isn't going to be in the format we're actually going to want to train models against, right? So we're going to write some components to perform ETL on this data and analyze it in parallel. The Hadoop runtime is going to schedule these by migrating compute jobs that operate on parts of our data to the machines that contain those parts. So unlike classic data warehouses, Hadoop enables scale-out storage and processing and provides a fairly easy way to keep our raw unprocessed data in distributed storage, along with multiple versions of post-processed and intermediate data. It's still not a great fit for a contemporary microservice-based application, though. Because Hadoop depends on having compute jobs co-located with the storage they're operating on for good performance, you won't be able to scale your compute and storage independently. And you'll essentially have to dedicate resources to both storage and compute. In practice, this means that a lot of Hadoop installations have to buy a cluster big enough to support all of their storage needs and manage it for a wide range of compute applications. Now, there's nothing wrong with that, and this is a great advance for distributed compute and storage, but it does prevent us from enjoying all of these benefits of microservice architectures that we were talking about. So the legacy architectures we've just seen have been enlisted to solve many problems, but tend to be more monolithic and less flexible than we'd like for running with elastic resources in the cloud. The architectures we'll look at next are more suitable for contemporary containerized applications. The LAMBDA architecture is an interesting approach to modernizing that traditional data warehouse. The idea is you have a stream of events arriving, and you're going to multiplex it to a stream processing layer and to a storage layer. The stream processing layer is going to perform imprecise but very fast analyses on the data as it arrives, characterizing your very latest data. Meanwhile, you have some batch jobs running against the distributed file system that are repeatedly operating on that data, performing precise analyses at a much higher latency. Finally, the most recent results from stream processing and batch processing are federated together in a serving layer, which presents users with a view of their data that strikes a compromise between latency and precision. This is suitable for microservice architectures, and the raw data remain available in this distributed file system, but it requires analyses to be implemented twice, possibly in radically different ways, as streaming algorithms and as batch algorithms. The KAPPA architecture was named in response to the LAMBDA architecture, and its design reflects significant advances in our message queue systems, stream processing frameworks, and understanding of how to develop streaming algorithms. The basic idea is that as you receive events, you put them on a message bus with a particular topic. So the component that will be doing ETL in another architecture is simply listening for messages on the bus with a raw data topic, and then writing messages with a preprocessed data topic back to the bus. So on for our analysis code, which reads preprocessed data and writes results. Our user interface components simply read the results topic. Now, this model makes a couple of assumptions. It assumes that our queues are durable and indefinitely replayable, and it also assumes that our problem can actually be solved by a streaming algorithm. We can solve a lot of problems with streaming algorithms, but this isn't a trivial assumption. So these are things to keep in mind. In my opinion, the most flexible architecture for data processing involves moving the data federation problem from the storage layer to the compute layer. Instead of federating unstructured data by storing it in a file system and defining ad hoc ETL pipelines, or explicitly structuring it on import into a database or ingest into a message queue, use a compute layer flexible enough to give you a uniform abstraction over multiple data sources. Trick question. Name such a system. Come on. Spark, right, unifies various data sources under the RDD and data frame interfaces, and it accomplishes this. So we've seen that Spark executors are essentially microservices, right? So we know we can run those in stateless containers. Furthermore, Spark lets us federate data from a wide range of sources. It's flexible and interoperable with other systems and supports both batch and streaming workloads. We know all this, but what we might not have thought about is that it's also general enough to implement the analytic processing part of a data warehouse, the compute component of a traditional data lake application, or a contemporary application based on the LAMBDA or KAPPA architectures as well. So once we're using Spark, we're set with microservices, right? Not quite. It is possible to misuse Spark in this context by deploying it as a legacy analytics workload architecture. If we build out a dedicated Spark cluster and we have several applications that depend on it, then we're really dealing with scheduling and multi-tenancy in two different places, since we need to make sure that the applications are running and responsive, but also that they'll have sufficient Spark executors for their compute. So this approach may make sense for applications with modest or sporadic demands of Spark, but there's a better way. Instead of having a monolithic Spark cluster that manages scheduling Spark jobs for several applications, why not incorporate actual or logical Spark clusters into each application so that they can be co-scheduled by the resource manager? By making the application the unit of scheduling granularity, we avoid having to coordinate between an application-level resource manager and a Spark cluster. And we're able to choose a deployment architecture reflecting that we're concerned with analytic applications rather than just capacity to run analytics workloads. Because our applications are composed of stateless microservices, we could even schedule them on separate Kubernetes instances, enabling us to achieve truly elastic scale-out for our compute requirements. As you can see, it's really crucial to get the architecture right if we want to benefit from containerized microservices. Now we'll cover some of the issues my team has had to solve in putting Spark into Kubernetes and into OpenShift, which is built on Kubernetes. So our unit of scheduling granularity is the application. And we currently build analytic applications in Kubernetes by incorporating a standalone Spark cluster in each application. We have a service that runs within these applications and that application components can interact with to request and provision standalone Spark clusters. The compute requirements of our applications can change over time, though. In this example, we have a single Spark executor over there on the right with a large task backlog even further on the right. In a traditional Spark deployment, we just use Spark's dynamic resource allocation to devote more executors to this app. And we can do something similar here. However, we also have a service that reads Spark metrics and interacts with Kubernetes to make more workers available to the application itself. So we can even extend elasticity a layer below Spark, requesting resources that weren't even there when we started the application. If you haven't used Spark's dynamic resource allocation before and you missed Luc Borlier's talk about it yesterday, check out the video when it was released. It's a really nice overview. The next concern we might have is security. For a little background here, let's consider what a container actually is. It's just a regular process, except it might be running in different namespaces than other processes on the same host. So my containerized Spark worker might have a different process table, file system root, and network routing table than other processes on the same physical host. But it's just a regular process that shows up in the process table for the host, or really for the enclosing container on the host. We can get a fair amount of isolation from other processes on the same machine just through this namespacing mechanism. However, if you pay attention to the state of container security, you know that ensuring you actually have enough isolation is kind of tricky, especially if you're running in a multi-user environment with potentially hostile users. If you're running as root in a container, you're still root on the host, albeit possibly with limited capabilities. So you really need something to ensure isolation beyond containers. In the case of Kubernetes, you can use Kubernetes namespaces to provide quotas for applications or isolation between applications. But currently, you need to be running on infrastructure that actually enforces isolation beneath the Kubernetes layer, like the Google Cloud Platform or OpenShift. In my team's original deployment, we had a networked POSIX file system living in the same rack as some of our compute nodes. A POSIX file system is great because you can use the standard command line utilities that you already know and love to access and manipulate your files. Furthermore, if it's close to your compute nodes, it's likely to be so fast that you almost don't have to worry about caching RDDs. However, a POSIX file system provides semantic guarantees that are hard to maintain as access scales out, and that aren't necessary for these kinds of applications typically. And it can also be difficult to manage access control for POSIX file systems. A second option is to use HDFS running outside your resource manager. This can be a great option if you already have a lot of Hadoop workloads, but want to develop analytic applications in Kubernetes that access some of the same data. However, if your compute nodes are scheduled as elastic microservices, it doesn't make sense to run HDFS inside Kubernetes. And if you can't co-locate your storage and compute, you lose one of the big advantages of HDFS. A third option, and the one we wound up going with, is an object store. There are a few implementations of the S3 API, including obviously Amazon's implementation, Swift from the OpenStack project, and Ceph. All of these offer fine-grained access control and are accessible from a wide range of client libraries. One downside to using object stores is that some legacy applications may expect a different consistency model, and another downside might be performance. Whether or not performance is an issue for you will depend on your application and how you actually use object stores. From our experience, I can say that once you're getting data from any service, whether it's an object store or a database, you can't say that you almost don't have to worry about caching RDDs anymore. If you missed Steve Loughran's talk yesterday, definitely check out the video for a lot of detail on best practices for using object stores with Spark. But a lot of people are successfully using object stores with Spark, especially in cloud environments or where you have an S3 compatible service on-prem. I came across this nice Quora answer from Reynolds Inn earlier this summer where he provided a careful explanation of how S3 can really make a lot of sense as a storage option for data processing applications. And I think that his answer applies nicely to other object stores as well. The last concern I want to talk about is networking. Because your containers don't necessarily have the same network interfaces and routing tables as other processes on the same hosts, there are three kinds of networking concerns that containerized Spark deployments need to address. The first is connections between containers, for example, between Spark workers and the master, or between UI components and the Spark driver. Some of the routing here is handled by Kubernetes, but our cluster management service also publishes a Spark master endpoint for the rest of the application. The second kind of routing is between application containers and other services running in Kubernetes, like databases. Have to have that state somewhere, right? We handle these with Kubernetes configuration. We can name the other services and then route to them by their names. The third kind of connection is between our application and the outside world. Administrators may want to view the master UI, so we publish a route for that to the outside world. We don't yet publish worker web UIs, but we will once we can take advantage of some improvements that will be landing in Spark 2.1. And end users need a route to interact with the application as well, of course. So we're really excited about Spark and Kubernetes, and I hope you're interested in trying it out too. Our next steps involve extending our initial informal performance evaluations, which have had some promising results, to more rigorous evaluations with more benchmarks and larger clusters so we can really understand how this works at scale. We also want to continue to refine and improve the developer experience with an eye towards continuous integration and continuous deployment. And finally, there's a really interesting discussion happening in the Kubernetes community right now about scheduling Spark tasks natively on Kubernetes without running a Spark standalone cluster. We've been part of that conversation, and we're looking forward to seeing what we can do to help out with that effort. So if you want to try things out yourself, here are 3 links. You don't need to take these down because I'll show you where to get them. But there is an example in the Kubernetes source code of running a standalone Spark cluster under Kubernetes. Our work on enabling Spark on Kubernetes and specifically on OpenShift is available through the radanalytics.io GitHub organization. And finally, that proposal for native Spark scheduling on Kubernetes that I mentioned earlier is in a GitHub issue, is where that discussion is happening right now. Thanks so much for your time and attention. I'll close by encouraging you to visit my blog linked here for more information, including all of those links that were on the previous slide. And you can reach me via GitHub or Twitter at willbe or via email. If we have time for questions, I'm happy to take them now. If not, I'm happy to take them offline.
Thanks for the presentation. I really like the concept of microservices, but more in the more traditional BI world where we have large enterprise data collections and a lot of integration up front for using the reports. How would you manage that by using microservices?
How would you do reporting with microservices?
How would you manage the complex integrations that we have to I don't know, about 200-300 mappings to integrate all the data and split that apart in part of the low.
Maybe we could talk about a specific example offline. I think in general, though, having Spark jobs that sort of process data and write to stable storage, and having a workflow of those is a pretty sensible approach in that case.
Thank you for presentation. Question. We hear more example integration with Spark and Mesos. Why?
Why do we hear more about it with Mesos?
Yes,
yeah, that's a great question. And Spark works really well on Mesos, and obviously, there's the heritage there from the AMP lab. I think you hear more about it because it's in the Spark source tree, right? It's one of the default options. It's a picture in the layer cake. Right? We didn't go with Mesos going forward because we had more local Kubernetes experts we could bother if something went wrong.
And if question which option best when we compare Mesos and Kubernetes for Spark, what you suggest?
I think really from an ease of use and a developer productivity perspective, I think Kubernetes is hard to beat. And I don't have any evidence that it falls down on a performance level yet, or a manageability level. So.
Thank you.
All right, that looks like it for questions. Thank you.